wish language models knew when to look something up instead of just guessing? Well, meet ReSearch. It's a clever way to teach LLMs to reason with search, not just from memory. Instead of giving them step-by-step instructions or labeled data, ReSearch uses reinforcement learning to help the model figure it out on its own. When to think, when to search, and how to piece everything together. The coolest part? The model actually learns to reflect on its mistakes, like realizing, oops, wrong search. Let me try that again. That's wild. In this video, we'll explore how it all works, how they trained it, and why this mix of reasoning and searching might be a big leap forward for LLMs. All right, let's dive in.
LLMs have become great at breaking down questions and reasoning step by step. But what if the model simply doesn't have the answer and needs to search for it? That's still a challenge, especially for questions that require multiple search steps. The framework introduced here is called ReSearch. It's designed to teach LLMs to think and actively search when necessary, almost like a student looking things up online in the middle of a test. Instead of using lots of labeled reasoning examples, the authors use reinforcement learning, or RLs. The model figures out how to integrate searching and thinking by receiving rewards when it arrives at correct answers. Check out the chart here. You'll see how this method consistently outperforms plain text generation, naive retrieval, and even methods like IRCOT. The improvements are especially large on trickier tasks, such as MuCK and Bamboogle, where multiple hops of reasoning are needed. Why does this matter? LLMs are already impressive at generating and reasoning, but they stumble when answers require fresh facts that weren't in their training data. Retrieval Augmented Generation, RAG, can help bring in updates from search engines, but it's not always ready for complex multi-step queries that need to be refined or repeated to get to the right information. Recent approaches let models reason in steps, showing their work in a chain of thought. That helps, but these systems still treat search like a bolt-on. They don't explicitly guide the model on when to search, or how to weave retrieved information back into its reasoning. Reinforcement learning changes the game by rewarding correct final answers without needing labeled reasoning steps. That's a big deal, because manually annotating those steps can be slow and costly. Some recent models have used RL to sharpen internal reasoning, but most don't integrate external search in a dynamic way. This is where the author's method comes in. They propose training a model to reason with search. Instead of being handed search results at the start, the model has to decide if and when to search, craft queries, and interpret results as it goes. Everything is trained via RL signals. Success nets a reward, missteps don't. They test it using two sizes of KWEN 2.5 models, and show it generalizes well, even if it's only trained on one dataset. How does this system actually work? It trains a model to reason while calling search tools when needed. This isn't just a simple retrieval step. It's done through RL, using Group Relative Policy Optimization, GRPO. Look at Figure 2 here. On the left, there's a set of answer candidates, rollouts. Each rollout is scored by a reference model, and those scores become rewards. The system normalizes those rewards across the group and then updates the policy. It also adds a penalty term, so that new updates don't drift too far from the old model, keeping things stable. But the real magic lies in how these rollouts are structured. Figure 2b shows a question broken down into parts. The model realizes it needs a piece of information, like a founding year, does a search, reads the result, and continues reasoning. Then it figures out it needs yet another fact, does another search, and finally completes the answer. Each part of the thinking process is tagged with less than think greater than, less than search greater than, or less than result greater than, making it very clear which component is which. This approach unifies the model's reasoning and searching into a single chain of thought. All of this happens via a reward signal at the end. No, manually annotated, here's how you should think, data is used. How does the model get better at this over time? It's all about RL with GRPO. When the model answers a question, it proposes multiple candidate responses. Each candidate is compared against the others in the group. This helps spot which one is best without needing a separate model to judge them. But there's a catch. You don't want the model to change its policy too quickly. So there's a clipping mechanism. If the new policy makes a particular sequence suddenly a lot more probable, the update gets clipped. This ensures things don't swing wildly. There's also a regularization term, using KL divergence to keep the new model close to the reference model. ReSearch goes further by mixing in real-time search results during rollouts. Whenever the model decides to search, the query is enclosed in less than search greater than tags, and the external system returns its findings inside less than result greater than tags. Then the model incorporates that info into its reasoning. Because the search results are not generated by the model, they're excluded from the loss function. Only the reasoning parts, the less than think greater than, less than search greater than, and final, less than answer greater than, impact the updates. To guide this process, prompt templates are defined. One set for base models, and another for instruction-tuned models. Both sets use the same basic tags, so the model knows how to think step by step, when to issue a search query, and how to finalize its answer. The reward is simple. If the final boxed answer matches the ground truth, it gets a high score. If it's wrong but the format is correct, it gets a small boost. If both format and answer are off, it gets nothing. Let's look closer at those prompt structures and the reward scheme. In the base model's prompt, there's a friendly user assistant style conversation. The assistant is guided to think. Inside less than think greater than. Search. Inside less than search greater than. Read the results. Inside less than result greater than. And then produce the final answer. Inside less than answer greater than. For instruction-tuned models, it's all in a single system prompt, but still uses the same tags. This consistency helps the model switch seamlessly between reasoning and searching. As for rewards, there's no hidden labeling of intermediate steps. The only hint is whether the final answer is correct. If it's right, the model gets a good reward. If it's wrong but properly formatted, it gets a small reward. If it gets both wrong answer and messy format, 0 reward. This setup encourages the model to maintain a neat chain of thought, even as it experiments with how best to solve the problem. Now the experiments begin. The authors train only on a dataset called MuCK, but evaluate on 4 benchmarks: HotpotQA, 2 WikiMultiHopQA, MuCK itself, and Bamboogle. These are all multi-hop QA tasks that demand multiple steps of reasoning. To keep things fair, they also ensure that no leaked data or overlapping documents sneak in. What happens after the model is trained on MuCK? They test it on all 4 benchmarks: HotpotQA, 2 WikiMultiHopQA, MuCK, and Bamboogle. Each one checks whether the model can handle multi-step reasoning using external knowledge. The search environment is open-ended, so the model has to decide how to query and how often. They compare ReSearch with a few baselines. One baseline doesn't use retrieval at all, relying only on the model's internal knowledge. Another tries a simple approach by appending retrieved documents to the prompt. Then there are more advanced methods, like iter-retgen and IRCOT. Those do use iterative retrieval, but don't integrate searching into a unified reasoning loop quite like this. To measure performance, they use exact match and also LLM-as-a-Judge. Exact match checks if the predicted answer text is the same as the gold label. LLM-as-a-Judge is more flexible. If the answer is correct in meaning but phrased differently, it can still earn a high score. The results? ReSearch consistently leads the pack. For the 7B model, it outperforms the best baseline by about 16 percentage points. For the 32B model, it's roughly a 15-point jump. They also test both base and instruction-tuned versions. The instruction-tuned versions do a bit better, but either way, the gains are impressive. What's really interesting is that training solely on MuCK doesn't prevent the method from generalizing. ReSearch holds up well across all 4 benchmarks. Now let's see a detailed comparison. Look at table XXX here, which shows performance on HotpotQA, 2 WikiMultiHopQA, MuCK, and Bamboogle. These tasks all require multi-hop reasoning and rely heavily on external searches. The table lists both exact match scores and LLM-as-a-Judge scores. You'll see ReSearch beating the other methods on each dataset. The 32B instruction-tuned version is especially strong on HotpotQA, hitting over 67% by the LLM-Judge metric and scoring high on the tougher tasks like Bamboogle. Then there's Figure 3. It tracks how the average response length and number of search queries grow during training. Early in training, the model gives short answers and doesn't search much. Over time, it realizes it needs to be more thorough, so it starts making more queries and producing longer responses. Figure 4 shows training and validation rewards steadily climbing. That confirms the model is truly learning something, rather than just memorizing specific answers. Notice how instruction-tuned models tend to write longer answers and carry out more search steps. They're more proactive at checking facts before finalizing an answer. Curious to see it in action? Here's a real example. The question asks, who won the 2018 presidential election in the country where Martín Ramírez Peche's political party operates? That's clearly not a one-step question. First, the model needs to figure out which country Martín Ramírez Peche's party is in. Then it needs to look up who won that election in 2018. The model starts by searching Martín Ramírez Peche. The result it gets back is noisy. Same name, different person. It recognizes the mismatch in its less than think greater than tags, admits the result doesn't look right, and refines the query to Martín Ramírez Peche political party. Now it finds that Peche is associated with the Labor Party in Mexico. Having pinned down the country, the model issues a new search query, 2018 Mexican presidential elections. That leads it to the correct answer, Andrés Manuel López Obrador. What's important here is how the model corrects itself when the first search goes off track. It's essentially noticing its own mistake and adjusting on the fly. All of this emerges from trial and error RL, not from explicit instructions telling it how to correct its own search queries. Finally, let's reflect on what this all means. The example above shows the model doing genuine multi-step reasoning, noticing errors, and fixing them all as part of a single chain of thought. There's no hand-coded script telling it how or when to refine its queries. It learned to do so from the reward structure alone. This self-elicited reflection is a highlight of the method. The model effectively scolds itself. Oops, that search didn't work. Let's try something else. That's the kind of adaptive behavior we want in an AI that reasons with external tools. In summary, ReSearch is a framework that trains LLMs to reason and search together using reinforcement learning, without any labeled reasoning steps. The search isn't just an extra plugin. It's part of the model's thinking loop. And over time, the model gets better at deciding how to search, when to stop, and how to piece everything together for the final answer. The experiments show it's not just overfitting to one dataset. It generalizes to multiple multi-hop challenges and learns useful behaviors like reflection and self-correction, all from a reward signal that only cares about correctness and formattings. That's the heart of ReSearch. Thanks for joining us today. Happy exploring!